So this video is going to be super useful for those who want to level up their knowledge on caching, because these problems are not going to be shown in any of the tutorial videos that you watch on YouTube or anywhere else. This is something that you come across when you actually have a production experience with caching. You have caching within your system and you're serving hundreds of thousands of users. This is when you're going to run into these issues, and I want you to be prepared and know what kind of challenges you may have when you have a cache within your architecture. So before that, I have to say that I already made 2 videos on caching. So the first one is exactly on this sketch, which is the caching strategies and their invalidation. And the second one is on caching headers. So go check them out if you're new to caching. This is like a prerequisite for this video. You're going to be well equipped, and those videos are really good deep dive videos. So you're going to learn a lot there. With that said, we're going to take a look at these 4 challenges that you are going to be exposed to once you have a cache within your system. And as I said, this is something that you're going to see once you have thousands of requests per second and you're serving hundreds of thousands of users. So you're working on a larger application, and let's say you're a software architect and you're responsible for organizing all of these bits and parts within your architecture. Now, we're going to start with the first one, which is the thundering herd problem. Now, when does this arise? So we're going to see that we have 4 different caching strategies. So a write through cache, where the cache literally sits between the database and the service. We have a write around cache, where the first write actually goes to the database, and then the cache miss always happens on the first request, but then we save this data that was requested to the cache, and all the subsequent requests are going to be fetched from the cache. And we have write back caches, which are literally saved to the database either on trigger or on schedule, but first they're always saved to the cache. Now we're going to be focusing on the write around cache, or cache aside, also a common name for it. And this thundering herd basically means that every time we try to get the data from the cache, for example, we're looking for product 42, and this is literally the notation that you have on Reddit. So you have a semicolon 42 for the ID of the product, let's say. And the problem here is that you might have literally 5,000 of requests running within the same second and trying to get this data from your cache. And let's say this data is not within your cache. Let's say 5,000 requests are firing here. So I'm going to say 5K, and this data is not in your cache. Now, the reason you have a cache is because you want to minimize the stress on your database, right? This is usually why you would want to have a cache, because otherwise you might just leave out the cache and let your database serve. But if you have a lot of requests going to your database, and especially if you're using a cloud technology and your database is a managed service, let's say on AWS or on Google Cloud, it's going to cost you money. Every request that your database is serving is going to cost you money, and eventually it might also become slow, right? This is why we have caching in the first place. But what happens if 5K requests are going to your cache and your cache actually does not have the product 42 yet, because it has never been requested before? So all of your requests are still going to miss the cache and they're going to go to the database, right? So how do we fix this issue? Well, we do this by a thing called mutex locking, or mutex/locking rather. Then the second solution is probabilistic early expiration and stale while validate. So mutex locking basically, or mutex/locking basically means that we are trying to lock this product within the cache. So only 1 request out of 5,000 requests are going to be populating the cache. So this 1 request is going to fetch the data and then put it into the cache, and all the 4,999 requests are going to be waiting for this exact lock to be released. All right. The problem here is that the other requests are literally waiting for us to populate the cache, but this is usually going to be happening fast. So you need to count this into the equation and see how fast you can retrieve the data for this particular product. If it's like a really complex join, then obviously don't use this kind of a pattern, but you get the idea. Let's take a look at the code. So as you can see, we have the bad example where we have no protection, but in the good example, so let's say if we have something in a cache, we just return the data, right, as expected. But now if we don't have the cache, so we take this lock key. So we put lock in front. This is the notation in Redis. We put the product, and in our case, product ID is 42, but let's put it as a placeholder, and we take the lock. So we put a lock, and as soon as the lock is acquired, so this is how you do Redis set lock key 1. This is just the value, right? What we do is we fetch the product from the database, then we set the value of the product to this product ID, and finally we return the data. So here's the product that we fetched from the database. And now all the other requests, so all the 4,999 requests are going to be immediately run against the cache and retrieve back to the server and back to the client. So you get the idea, right? Now, another solution is a probabilistic early expiration. So the reason this issue happens is because, let's say, product 42 was at some point in the cache, but then the TTL, so time to live within the cache, there's a specific window within which the data is in the cache and then expires, so it gets deleted. For some reason, product 42 was very popular, and as soon as it's expired, we got thousands of requests, right? So what you can do is kind of retire this product earlier or delete from the cache a little bit earlier before you know that it's going to become popular or hot. But usually you cannot predict what time of the day or when exactly your cache is going to be needed the most. And we also have stale while or validate, meaning let's say we have these 5,000 requests, right? So we take only one request that's going to be doing all this hard work, going to the database and then repopulating the cache, and the rest of the requests, so 9,999 requests, are going to be returning just stale data. Okay, they're just going to be returning the stale data that we already had in the cache. And while this one guy does all the job, it's going to update the value in the cache. So there's no reason to show this example. I hope you get the idea. If not, write me down in the comments. All right, so we have another example, which is cache penetration. And this is usually happening when somebody is actually trying to attack your system, right? It's usually bots. So they're going to send thousands of requests into your system. Let's say they're trying to fetch product 42, or let's say even user 6, right? And user 6 doesn't actually exist. And they're also fetching user 7, right? User 7 also, or user 50. Like they're sending thousands of useless, meaningless requests to just bring your system down. And what happens is that this is going to result in a huge amount of requests. So first, this is going to go to the cache. Then cache says, I don't have this. Then the request goes back. Then the request goes to the database. Then the database says, I don't have it either, because these users that literally don't exist. This is a hacker's attack on our system. So instead, what you can do is use something called a Bloom filter. Now, Bloom filters are really cool. And there's a really good article on this website. I'm gonna link the lists or link the links below in the description so you can read about them. But basically, Bloom filter is kind of an algorithm which is going to say probabilistically whether this user exists or not. So let's take a look at the code. I'm gonna go to penetration.js, and you're gonna see that we are having a key called Bloom and a Bloom key. So products semicolon Bloom. And what you're adding is actually native to Redis, so you can do this too. So bf m add Bloom key. So these are the users that we know that are valid IDs, okay? And then when we use the Bloom filter, we're going to send a command. So we're gonna say Redis send command bf exists Bloom key, and with the ID that the bot is requesting. And the Bloom filter is gonna be super fast, all right? So it's going to check, and if it's definitely not in the DB, it's gonna say no, it's going to say false, all right? And we're going to skip everything. If it's in the DB, it's going to return the data. And Bloom filter is literally like a statistical algorithm that's not going to go through over your thousands or millions of entries within your Redis database or Redis cache. It's going to do a probabilistic calculation and tell you right away whether there's a chance that your users might exist, or the requested user might exist in the cache or not. If it's there, then it's going to return it. If it's not there, it might return it, so it's still probabilistic, but it's most likely gonna say that no, it doesn't exist. And this is how you're actually going to avoid the round trip into the database, because your client is gonna get this, or your service rather, gonna get this result called Bloom filter and data null. And this is going to be the flag for you to know that, hey, I actually don't need to go to the database anymore, right? My Bloom filter already told me that this user doesn't exist. Another way to overcome this would be actually to populate all of your users with null values. So let's say you have a user and a user ID, and if it's cached because you already pre-populated all of your users with null, then we're gonna return none, all right? Meaning if I get null from the cache, then I know that it's not in the database either. I don't have to go to the database. Okay, this is how you can overcome this. Now the third one is called cache avalanche. Now the cache avalanche is happening when it's kind of similar to the first one, so thundering herd, but it's happening when a lot of popular keys, some orders, some users, so some transactions, and all of them, they're all very popular and they're all expire at the same time. And this puts a tremendous pressure on the database. So how do we fix that? Well, we can fix that by something called TTL jitter. So meaning when you assign a TTL, so every time you put something to the cache, right, you usually assign a TTL. Yeah, here's a TTL, for example. EX is basically expiration time. And this is 300 milliseconds, right? After 300 milliseconds, my value is expiring. The data gets deleted from the cache, basically. And with a jitter, what you can do is when you put something into the cache, don't use the same exact TTL for all the values. Make them somehow random, okay? As soon as you randomize, the chances of all of them being expired at the same time is obviously shrinking. And this is what you can do. And also make sure to use custom TTLs for different types of things that you cache. So for example, for user profiles, you can cache them for 24 hours because they rarely get changed, right? Inventory counts, like if your inventory changes, obviously this happens very often within an e-commerce website. So you can set this to 60 seconds, meaning very low. So you get the idea, right? And we have the last one, hotkey problem. Now, all of the things that we discussed so far, thundering herd, penetration, avalanche, they are usually happening within the right around or cache aside pattern, right? These three other patterns are not susceptible for it, but the hotkey can actually influence all types of caches, all right? And let's talk about the hotkey. What is a hotkey? It's basically a disproportionate share of shard reads for some keys. Okay, so every time you store data within Redis, it's being sharded under the hood. So let's take a look. Let's say we have a key called product viral, and viral is literally the ID of the product, right? What's happening is that when one of these IDs, in this case it's called viral, gets viral or becomes a hotkey, let's say, and all of the requests are requesting this same exact key, our Redis is going to suffer, okay? Our cache is going to suffer. So what we can do instead is actually make sure that product 42 is not saved only once within Redis, but let's say it's saved 5 times, okay? Well, does it make sense to save it 5 times? Well, turns out yes. So after the product ID, we can add the shard ID. So let's say this is going to be 2, this is going to be 3, and 4 and 5, right? You get the idea. Now, when we retrieve the data, how do we know which shard we're going to pick from? Because we don't know these IDs yet, right? Well, the thing is, when you try to read the data, you have to know how many shards you had initially. So let's say in this case, we know that we always partition the products, or we always shard the products in 5 different shards. So every time you make a request, you just pick one random number, okay? So this request, let's say, is picking a random number 2. So this is going to pick this value. The next one is picking, let's say, number 5, and it's going to go into this shard, all right? This is how you can distribute the load between your values. So you don't have to always target the only shard. But again, keep in mind, this is something that you need to do once you have, like, let's say 50,000 requests per second. this is like YouTube level, right? This is something that you're usually not going to run to, but I still want you to know that these things exist. And let's take a look at the code. So we get the replica key, and with some random math manipulation, and we know that we have 5 replicas, all right? We declared this. So we have 5 replicas, meaning we have 5 shards, and the key is going to look like this. So let's say this is the product, semicolon, replica, semicolon, 3 or 1 or 5. So 1 to 5, basically. And we're trying to read this data. If it's cached, then we return this data. And by the way, when we update, we also need to update all the partitions. So we need to update literally 5 entries within our cache. But if it's not there, meaning we need to write it into the cache. So this is how the data is going to look like. We loop through partitions, meaning we have to update all of these partitions. So it's a bit of overhead on the write level. Keep this in mind. And we're going to be updating all these partitions. So from 1, 2, 3, 4, 5, or actually 0, 1, 2, 3, 4 with an expiration date 60. All right, guys, this is everything that I wanted to tell you. If you have any questions, let me know in a comment. I will try to do my best to answer those. Otherwise, I'm going to see you in the next one. Goodbye.